Okay, so when trying to solve the which is more acidic here early on, there's a couple ways to do it. Probably the easiest way is just to know the pKa's of the various different acids listed here. And that's what I did. I've listed them as strong acid on the top, weakest on the bottom. So the carboxylic acids are definitely the strongest acids of these. But the only ones of these, there's only the first three are the only three that actually would fit into the category of even weak acids. All the others are actually outside of it. What I wanted to do here also was to show you how we could estimate it, and actually even so we can expand on it some, which is what we're trying to do in the book if we're explaining on how some of these relationships are developed. So what I'm going to do is we're going to talk about some things that we know are strong acids, and we're going to have them related right to the periodic table. And what I mean by known strong acids, I'm going to relate HF to HCl, HBr, and HI. Now we know from general chemistry that HI is the strongest of these acids. And actually HCl, HBr, and HI were all considered strong acids, just so happens HI is slightly stronger. Now, we actually can get pKa's for these to rate the strengths. And I get a pKa of the HF of around 3.1. HCl is actually -8. And both these are in the tens, depending on where we find them. And these were the two most consistently found values, 10.3 and 10.7. So they're not exactly the same, but the negatives are a good indication those are strong acids. All right, to complete this thought process, though, I'm going to go across. Now, OH, for instance, part of water, I'm just going to do this table as if everything is H's. So even NH, I'm going to assume all the other locations that the nitrogen can handle is H's, and CH, everything around there is H's. All right, so we're looking at just that H bond there. And if I find the pKa's of these individual things, the pKa of water is actually 15.7. NH3, it's actually around 37. And OH, or the CH4 here, is going to be approximately 60. It's a true estimate. We don't even really have a good number for it. But we can say, ooh, there's a weird dash. We can actually say in all cases a CH where the carbon is just bonded to three things is right around 60. And I'm going to change this some and say, well, if it's a NH where the nitrogen is just connected to something else, instead of saying 37, which was what ammonia is, we're going to actually say for any NH attached to anything else, it's around 40. And complete this thing. Get rid of that big eraser mark there. To just OH, where the O is just connected to something else, instead of saying 15.7, we're going to say it's about 15. Now where this comes into play, that says that any alcohol is going to have a pK around 15. Any amine, I'm going to write down these names here, is around 15, around 40, and this is what we're going to see is called later on alkanes. Alkanes just have carbon-hydrogen single bonds, and that's where these numbers come from. So that, this, and this. All right, but as we can see on the trend, strong acids are down below, and we get weaker as we go up and weaker as we go left. All right. The next thing we want to do is look at the situation where we can have double bonds or more S character. Now, I can't do that really with oxygen because oxygen can't make really an easy double bond that's stable because both its extra electrons are here in lone pairs. But nitrogen, I could have a situation where maybe both those bonds are going to the same thing, and I can definitely see that on carbon. Well, it turns out when that makes that double bond, it does significantly lower the pKa. For alkanes, a carbon-containing compound with a double bond, going to be the alkene family, drop my L, and that actually drops us down around 20 units each time, and this actually brings it down to around 45. And we will see the same thing happens here. Matter of fact, this isn't even part of this chapter, but in later chapters we have this cool little feature that pops up. So I have a 5-membered ring that has a nitrogen in it, where these are all just carbons and hydrogens. And this has an H on it. This molecule like this is called pyrrolidine. Big long name. Has a pKa of 36. Almost exactly where any amines are found. Alright, but see how this double bond is? If I take this molecule, rip off some hydrogens, and make this an aromatic molecule, the double bond moves around, so I'm going to put a little circle here. That's how we end up drawing it. And what that kind of means is there's a double bond temporarily here, and ooh, I did that as a 6-membered ring. Wrong structure. It is a 5-membered ring. But the little resonance structures, the double bonds are here and here sometimes, here and here sometimes, here and here. And basically they just move around, which is why we end up seeing this drawn with a circle. But because that nitrogen actually is part of a double bond, it makes this bond tighter, or pulls those electrons in closer, which allows that H to get ripped off easier, and our pKa is about 16. So just by putting that pi bond adjacent to where the hydrogen we're talking about is, you make it more acidic. And same thing happens with the carbons. If I have that pi bond right next to the position we're talking about, it makes it more acidic. The pKa drops. And if I do that one more time with a triple bond, so 2 pi bonds, the pKa drops down to 25. So we're going to see this all the time. When you're looking at an atom bonded to an H and you want to know how acidic it is, you really can look at what atom we're talking about in the pKa to get you a starting point. And it really is going to be the -10, 8, 3, then 15, 40, and 60. And then once you get that ballpark range, you look how this is connected. If it's all single bonds, it's just these pKa's that you find from that periodic table layout. If there's a double bond, you're going to knock approximately 20 off there. If there's a triple bond, you're knocking off approximately 30. We'll go with that nice round number. But it actually makes it more acidic. Now, another term that throws people off. And our book is guilty of it, just like almost every textbook you'll find. They'll talk about high acidity. Well, high acidity is actually a small pKa. pKa's get smaller and smaller the stronger the acid it gets. So I try to, on my question, I'll ask for high pKa, and we're talking about the least acidic there. And we'll talk about most acidic, and if I use most or least acidic or basic, this is most acidic up here, and this is least acidic. All right, hopefully that clears up some of the difficulty.